Hey, John here. I'm trying to work on a Verilog design that involves the inputs from this particular timing diagram, and I want to work out a test bench that is a realistic representation of this portion of this bus that takes place. This is a Z8S180, but that's not relevant for today's topics. Today's topics are if you have a system that's documented in this manner with a waveform diagram, and they give you all these times, this happens here and that happens there. What's a reasonable way to do this? And hopefully what I have to show you today is a reasonable way to do this. I would love to hear any comments from anyone in any way as to whether or not there's a better way to do this, because it took a little while to kind of figure out. And I certainly hope it's useful for as a technique that anybody can use. A big thanks to everybody, all the likers, subscribers, commenters, and supporters of my channel. Thank you very much, especially the VIP patrons listed here. See the Patreon link below or in the description of this video if you too want to support my channel. Thank you very much. All right, so the reason we're looking at this is because I've been looking at this a lot lately, and I've been flipping back and forth in the manual. There's a couple of pages. There's this diagram and then previous pages before this. It tells you, if you have this version of the chip or that other version, or you're running it at 3.3 volts or 5 volts or whatever the rules are, the actual values, the actual times that you can count on between, IO rec going low after this thing here happens, these times change. So in this diagram is reasonable and correct, but it can be very confusing since all the times are around 20-some nano, and almost all these values are 20-something. These are the ID numbers of which time spec you're supposed to look up in tables in this manual. So I annotated it once and for all on one page, because as I was writing my test bench, it drove me nuts. So you might want to try this. Step number 1, get a diagram that's representative of the problem you're actually trying to solve. And today what I'm trying to solve is, all I want to do is recreate this timing diagram in a Verilog test bench so that I can connect it to modules that I'm designing. I don't care about the modules today. That's not relevant at all. It's just, how do we take this timing diagram and express it in Verilog in a way that's kind of readable, understandable, and if I make adjustments to it, the whole thing doesn't fall apart and everything starts moving around in weird ways. All right, so what I have done, we're not going to look at the rancid. That was my first draft. We're not looking at that. That was terrible. So here's what I've come up with here. Now, I've talked about these test benches before, and I've been a little bit cavalier about certain things. Sometimes things matter, and sometimes they don't. So there's no hard, fast, right and wrong way. But if you are writing Verilog, you're very serious about this, you have a fairly complex project, and it is growing and becoming more and more modules in there, you may want to put more effort into treating your test benches with all the same rigor, I guess is the word I'm looking for, as your actual modules themselves. Like I said, I've been a little bit cavalier in the past. Let's rein it in a little, okay? So let's start at the beginning. And you're at a test bench, you've got a bunch of variables that you're going to use. You're going to assign these values over the course of time, over the course of simulated time, to represent your system's activity. And in the Z80, or the Z8S180, I should say, in here, in this diagram, there are signals that I care about. There's phi. This is the free running clock that the CPU runs on. There's the address bus, there's the IO rec signal, and the write signal, and the data, in and out values. Specifically, I'm looking at a write and output operation that concerns the IO rec. This has to go valid to let me know I have a valid address, and write has to go valid to let me know I got valid data, and the phi clock and the relationship to these, trailing edges on IO rec and write. This is when you want to make sure you have your data transfer take place. during or at the end of these rising edges here. Now, as you can see, these are in reference to the tables above, and the chicken scratch version of this that you just saw is the one that I have worked out with the actual values on it, which I've transcribed into here. Okay, so let's look at this. We're going to start out. Here's my IO rec, my write, my data bus that I'm going to use as an input in this scenario, and the address bus that I'm going to use as an input in this scenario. Now, the Z80 is an 8-bit data bus. I'm only caring about input in that it is an input into the FPGA, logically speaking, from the CPU, which is externally to this. So I think of that as an input data bus for the purpose of this test bench, as well as the address. The address comes in. I'm only dealing with 8 bits of the address bus for the old school style I/O operations, which used to be 8 bits on a regular old Z80. You can use 16-bit I/O operations on S180, but that's not my concern right now. So we have an address bus, we have a data bus, we got the I/O rec signal letting us know it's an I/O request, and we're outputting from the CPU, inputting into our FPGA. Here's my phi clock. Now I also have a T1 marker that is for my own sanity, because when you generate this, you just have clocks ticking and stuff happening all the time. You need to know without any confusion whatsoever when these T1 cycles take place. So you always have your bearings. I want to know, is this the one or is it supposed to be the one? I can know when it is the actual one specifically without inferring that it must be, here, there, or wherever when I plot the output of my test bench. So I throw this in there for a reference. There's some other signals like PIX clock and these other things that are related to these modules that I'm testing in this particular case. None of this is relevant today. I'm going to just delete all that from the waveform output. We won't even look at that. All I care about is expressing the order of events that take place as described here, so I can use this as inputs into the modules that I'm testing downstream from the test bench itself. So, okay, what do we got going on here? I have a phi period and I have this other clock that's running. That's not important right now, but if you have clocks, and I decided I wanted realistic timing. I mean, in a lot of ways, you don't care that my actual target is to run at 18.432 megahertz. Who cares? You could simulate it at 1 megahertz relative to everything else, and all the timing relationships would be the same. The actual times would be wrong, but the relative order of operations and closeness in time, relatively speaking, to the clock and so on would still be the same. But I decided I want the scale, the ultimate scale in the waveform up here, like you can see here, 300 nano, 400, and here's my T1 marker. You can see that over there. The duration of the period of the clock is going to be whatever this turns out to be, on the order of 50 nanos or so. My point is, I wanted to know what that was going to be, and I could get realistic values. So I'm going to create a free running clock. I've shown you this before, and I'm going to do it like this. I'm going to use the period divided by 2, because remember, 180 degrees of that period is high, and the other 180 is low, and the thing just toggles up and down, up and down, up and down. Now, whether you use a blocking or non-blocking assignment in a trivial always block like this is probably not a huge deal, but it might be, depending on if and how you use the phi signal in your various modules. Since the phi signal should only be used in a sensitivity list in an always block or something like that, you should be okay either way. But I'm going to use non-blocking assignments for everything in here, because while it might not matter in some cases like here, it will matter in other ones, okay? All right, so what are we doing? We're waiting 180 degrees of my clock, and then we're going to then invert it, and then wait 180 degrees and invert it again. That gives me my free running clock that you see up here, phi, right there, going up and down in continuous time, okay? So these are, of course, values that are all reg type up here. I initialize them to 0 or whatever I want them to start out as up here. And I do it here. Sometimes I'll do it in the initial down here. Sometimes I do it at top. I'm moving on to always doing it up top up here. And the reason, my rationale for this is that I want these to start out at 0 before any always block here, or this is a special kind of always block that only goes once and then stops, right? All these need to have those values before any of them start. And you don't really know which one's going to go first, which is the blessing of how Verilog runs its always blocks. It could be this one, could be that one, could start the initial block. It could be an initial or an always block in this module under test. It could be an initial or always block in this module under. How do I know? Nobody really knows. And if something uses one of those signals right off the bat, there could be a problem. But if I do it up here, it's assigned before anybody does anything. All right? Now, I set reset here, and I wait a little while, and this is dubious. I'll explain that in a minute. And then I turn off the reset signal here, and then I move on my merry way down here. I point that out because reset is used in all my modules to reset the module itself. So even if this thing does start up in a messy, glitchy sort of a way and things are all junk, the reset will flush it out, or it should anyway, right? It should flow through all these modules and get them into a known working state, even if I don't preset all these things, okay? And if you think about it, you need that anyway, because when you run it on a real FPGA and it wakes up, yes, it'll wake up in a consistent state because an FPGA is really a RAM device and all these things have values all the time. But an ASIC will start up in a very random state because it just powers on out of nowhere in raw silicon, where an FPGA has a program file that comes in and all the D latches and things like that are programmable inside your startup boot file, and will always start up in a consistent way when your FPGA resets. So if you're designing to build an ASIC, you definitely want to have a reset to reset all your stuff. Anyway, okay, so that aside, I think I beat that point repeatedly on my other FPGA videos. Okay, so what's dubious about this? So this looks a little bit like how I very often write my test benches. Let's look at what the difference is between this and this, okay? Let's start with this. Let's say you wrote this. What happens? Well, there's no delay here, and this starts when the simulation starts at time 0, okay? Which means that should the simulator decide to run this initial block before it runs an always block here, or an always block there, or an initial or an always block in here, or one in there, if it decides to run this one first, then this reset will be assigned a 1 before anybody else sees a reset assigned a 1. Okay, but if it doesn't do that, then some other initial block or an always block here or in some other module could fire up and reset. Might have unknown, or it'll have whatever it says up here, which is actually 0. Okay, it could have anything in it. Who knows? Now, if on the other hand I do this, okay, ignoring everything else down here, if I do that instead, then what I do know is that everybody's initial and always blocks will start in random order, because that's the rule. And when this happens, the reset will have a non-blocking assignment of a 1 to overwrite the current value, which I just showed you was 0. This guarantees that every single initial and always block that wakes up and decides to execute code at time step 0 will see the reset signal with this value up here, which is 0, which is 100% consistent no matter what happens in the random startup of all your blocks. Then, at the end of time step 0, because it's non-blocking, it will schedule the change of the reset from that 0 to a 1 after everybody everywhere has had a chance to see and use and consume the reset and its code at the current value, which was 0. This is an orderly way to transition from a 0 to a 1. This is why you use it in synchronous circuits, that it being the non-blocking assignment, so that it happens in an orderly fashion, so that when you do a simulation, you don't have this weird thing where, well, if this one goes first, then it'll be a 1, but if the other one goes first, it might be a 0. No, that's just bad. And this happens over and over throughout all your code if you don't use, if you don't really think this out. Now, you can write your test benches, and normally I do, in a way where you don't have to resolve that confusion in your test bench itself. For example, sometimes I'll put a one time step delay up here, or a couple of time steps of delay, so that I can guarantee that reset changes at a time where nothing else is looking, between two clock edges or something like that. It has the results of creating a reset that will take place in your waveform diagram, in your test bench output. When you look at the waveform viewer like this, it would have a tendency to shift this edge over a little bit, which is actually, arguably, and I've always thought of that as being far more realistic than seeing it go low at the exact same time, say, of some clock edge. All right. Well, it might go low at the exact same time as a clock edge. If you have a cause-effect situation where this falling edge results in this edge here taking place and changing its state, then you can know 100% certain that this falling edge had to come first, even if the waveform diagram shows you at the same time like this, or even if your simulation would show you a situation where the two take place at the same time. Okay, so by using a non-blocking assignment, I can know that while this takes place at some time step, which is going to be 4 periods into my simulation, if that happens to coincide with something else that takes place at that time, is my point. I know what the order of events are going to be. Okay? Now, this is probably not a good idea anyway. It's okay, but this style where you do something and then you wait and then you do something and then you wait, that's, you can certainly do that, but it turns out it's kind of hard to maintain your code. So I've decided I'm going to use a different technique. We'll see down here. Notice when I do a non-blocking assignment, I have a delay over here. Now, I haven't talked about this, I don't think, before. I may have mentioned it more casually earlier on, but on this test bench, I'm using it in a style where it's easier for me to convert my waveform diagram to this test bench, and that's really why we're here today. I used to have just a bunch of delays and things that change over the course of time, and some of them were blocking and some of them were non-blocking, and it turned into a mess. I mean, these things grow, they evolve over time, and usually what happens is if you're serious and your project moves on long enough and you have to take it seriously, you got to clean it up. And I've been cleaning this one up today, and that's why I thought maybe I should mention some of these things to make sure that we're all in sync on this. Okay, so this is okay if you really do want to waste time and then do something and then waste time and then do something else and so on. That's one style of doing something. Another one is to put what looks like a sensitivity list, and it basically is. So normally you'd associate this with an always block. Now, I haven't done these in test benches that I recall on my channel because a lot of them are not really timing based. They've been very basic, simple test benches in, combinational circuits mostly, sometimes sequential circuits. But this is pretty important when used with these non-blocking assignments. And this sequence of things here is what makes, in my opinion, this test bench more readable than what I used to have, which was just a lot of stuff like this, okay? So let's look at this a little bit more closely. All right, remember I'm modeling this I/O cycle here. It's got T1, T2, T-wait, T3. This is what it really is, okay? There's 4 cycles, and that's what they're called. In the first cycle, somewhere in the first cycle, the address bus goes stable. Somewhere in the second cycle or somewhere around here, I/O rec goes low, then my write goes low, and you can see these are basically cause-effect arrows with a delay saying that on the rising edge of T2 will cause write to go low within so much time, and they put a 22 there, and you look up the 22, and you find out that really means that this amount of time is less than or equal to 25 nanos. So it turns out write can go low as late as this falling edge if you're running at 20 nanoseconds, because it will be 25 nano high, 25 nano low. Okay, so this diagram can be somewhat misleading because they draw the edge way over here, but it really could happen as late as, on this falling edge. And that's why we want to make sure that our test bench is realistic, okay, and includes the extreme worst case values. And that's what we're going to see here. So I'm looking all these things up, right? So what do we got? We got I/O rec is number 28 after the falling edge of T1. I look at my cheat sheet over here. 28 over there is less than 25 nano. So this could happen as late as the rising edge of T2 and most likely after T1, if I am reading this correctly as a cause-effect type of relationship. They don't say that 0 is the minimum. They leave it blank, which, look, we're trying to make sure that we got the details right here, and they don't even give you a minimum. They only give you a max. But, okay, I'm pretty sure that the falling edge of T1 is what causes this to take place. Otherwise, they would measure it off for some other time. Okay, now number 7 here is like 5 nano. It says this will be, 5 nanos is the minimum amount of time that the address bus will be stable before I/O rec goes active. Okay, so you can figure out when this is, even though it gives you no reference to the phi clock at all. I'm sure this changes in result to the rising edge of T1, just like it does over here, which is whatever it's got a number 6 after the rising edge of T1. You look up a number 6 and you'll find out that that is at most 30 nanos. So this could actually change all the way over here after T1 has fallen if you're running at 20 megahertz. So I suspect it could be way over here, but they do guarantee a minimum of 5 nano before I/O rec goes low, and I/O rec goes low at a maximum of 25 nano after here, which is actually here. So the latest that you could see the address would be 5 nano before this rises, which is actually 40 nano after this. So that's actually outrageous compared to the time here where it says 30, which also felt outrageous to me. So yeah, this is about the same kind of a thing going on there. Now, I don't ever expect to see it hit the worst case, but I want to model it to make sure that what I'm doing, and I want to count on it, will still work even if we get the worst case values. All right. So the first thing I wanted to see in my simulation, we come out of reset, we just let the clock run for a little while. Then I'm going to mark T1. Again, here's my final product here. This is the T1 marker. All right, that guy right there represents this T1 right up here, okay? And the address bus, we can zoom in a little bit here. The address bus here should go active sometime after the rise of T1 and sometime before you see the I/O rec go active here. Now I drew this positive logic while this diagram up here has negative logic, so don't let that throw you. nominally it's going to go, the address bus should become stable about there, and IO rec, because it happens after the falling edge of T1, like I said, and before the falling edge of T2 at 20 megahertz, it should be, you know, somewhere in the middle, so I stuck it in the middle. All right, now what's next? Down here we have the write signal, and the write signal, when does that thing do its game? Write will be number 22 after the rising edge of T2. We look up number 22 on the old cheat sheet, and we see it's less than 25 nanos. A lot of these are just less than 25 nanos. So what does that mean? It means that it will go active before or with this falling edge of T2 if we're running at 20 megahertz. I'm only running at 18.4 something megahertz. So it turns out that whenever these are 25 nanos and they look like they may overlap and coincide with these edges here, mine will go slightly ahead, okay, given those guarantees. But I'm going to assume that my worst case is that I'm running at 20 megahertz instead of slightly slower, okay? Just for a mental picture in my head. My timing diagrams up here are actually going to be accurate and correct, even in the worst case scenario, which I think is over here, in that these things will happen if we zoom in a little bit here. For example, this is your 25 nano after the rising edge of T2, which is ever so slightly before the falling edge, because this thing here, as you saw before, is not running at 20. It's slightly slower, which means this is a little bit longer, so mine will sneak up a little bit early, okay? Now, while we're here and we're looking around, sometimes you see a white line in here, and sometimes you see a white and a red line. If I hit my middle mouse, let's highlight the right signal here. First of all, if I use the left mouse button, what I'm doing is dragging this thing around. And you'll notice as I come by an edge, it kind of tries to lock onto that edge a little bit. It moves relatively fluid here, and then it kind of stops to kind of snap to grid right there, okay? Now, the same thing is true about the white one. If I hit the middle mouse button and slide it around and let that snap to right there, release my middle mouse, and I got a white line. What I see up here is the distance between the white line, which is B, and the red line. I got 35 nanos to the right of B. So I can go like this now, and it can see that that's 2 nanos. Now, 2 nanoseconds, I'm trying to zoom in here. Whoa, I'm really close. Ah! Now I reset my... Okay, all righty, we're having fun now. Where's my scroll bar? There it is. Oh, my gosh. Woo, okay. 2 nanos is not a very long time, but it actually is pretty long in an FPGA's life, because they can run pretty quick. Now, as a setup and hold time, I think that is probably palatable inside the FPGA, but because this signal is actually coming from the Z80, S180, and it's going over a circuit board and in a pin, there's capacitance, inductance, the reactance garbage, the noise on the signal. This is probably not something I ever want to really count on, okay? It's also the worst case. In reality, the right signal is going to happen way over here sometime, 99.9% of the time. But in keeping with, it could be as late as here. My point is that if it is this late, I may not make the setup on this falling edge, and I may miss it. Something could go, metastable on me in my design. So, and this is one of the reasons we look at these waveforms when we do our test benches, okay? Now, where were we? We're doing I'm going to do 2 cycles. I'm going to have one that's reasonable and middle of the road kind of timing that I've seen on my oscilloscope before, which is probably going to happen more often than not. And then I'm going to do another cycle that's the absolute worst case, where the IO rec and the write happen really late, or they go up and end as early as possible. They give us the narrowest window of opportunity, which is the worst case that we have to care about when it comes to consuming the data that's written into our FPGA implemented IO device. So here's the moderately, middle of the road variation of this whole thing. Now, I'm not sure how often I've even talked about these in my channel here when we're talking about FPGA test benches and stuff like that. These are incredibly useful when you're trying to express changes of state relative to a clock, which is why the language has these in the first place, right? When you use them in your synchronous circuits that are in the always block, right? You always at, when you give it a clock and stuff like that. Well, you can use them right in line like this. You can't do this, obviously, in synthesized code, but in simulated code, what this means is wait until this happens. Then proceed. Okay, great. It's the same definition in the always block when you use them in your real modules, in your synthesizable modules. Wait until that happens, and when it does, execute the body of the module. It's a while loop. It's forever, do this, and wait for this to take place, then do all the stuff down here. And then what we're going to do is say, wait for that to take place. It could be something else. Do this, wait, do, and so on. So now, and this is kind of a big deal, and this is really why we're here today. This and these non-blockings, okay? Now, what I've done here is you can think of this a couple of different ways. This is like unwrapping an always block loop. If I wrote an always block, and the first time through the middle of the always block, it did this. And then the second time I went around the always block, it did this, and so on. I'd have the same thing. And I could actually write that. I could put a counter in there, and I could say if the count equals 1, then execute this. Else, if the count equals 2, execute this. If the count equals 3, do this, and so on. Provided that I'm always going to wait for phi. Yes, I could do that. And this is an unrolled loop with a bunch of if and else's. That's one way to think of this thing, all right? But notice that I got now I got a pos edge of right, and then I got a pos edge of phi, and what else? And some other weird wonkiness going on down here. Okay, most of the time I'm just saying pos edge phi. Okay, sometimes I say pos edge right. This is why you can't just make it an always loop with an if, because sometimes you want to wait for something else. Okay, so the takeaway of this part is you can just throw this in, simulated code, and the simulator will wait until this happens and then proceed. Now, this is very, very different than a lot of my test benches. I write things that look like this. Wait until I know there's a pos edge on phi. I can do that. I know that phi starts out as a 0 and it's doing this. So if I wait a whole clock period, like right here, I know that this will take place on a positive going edge of phi at 4 steps in, 4 edges in. Let's see if I got that right. I might have it upside down in my head. Let's look over to the left here. Oh, it's a negative going edge. Oh, that's because it starts out low. Yes. I mean, if we zoom way in here, you could argue that this whole thing starts with a negative going edge on phi because it starts out low rather than high. And what happens is, where are we at here? We say reset equals 1 here. This is in time step 0, even though it starts out as 0, and then it sets it to 1. I would argue that it did start out at 0, and it went high. You probably, I don't know. Maybe arguably there could be a rising edge sneaking in this waveform diagram here. But like I said, usually when you start up your entire simulation, you got to deal with glitches and stuff like that anyway. So I go from 0 to a 1 in time step 0, and at the end of time step 0, reset is equal to 1, and that's what this waveform here is showing. So it is correct. Okay, then I wait 4 periods, and then I go to 0. So that's a full period. So there's 1, 2, 3, 4 full periods, and it's on a falling edge because, like I said, in my mind, for some reason, I was thinking that this was starting high, but it's low. That's exactly what we got. And this is another good reason why you should put this in your code. because I reset it 180 degrees out of phase from what I thought it was. If I just waited another period here and just declared, okay, I'm now at the place where T1 should be rising, I'd be wrong. And I could, of course, correct that by waiting for a half a period and then have it rising here. I mean, that's a bug, all right? But it goes to show one of the values, and not a huge value, one of the benefits of this notation here. Now, I laugh now because it's trivial to fix, and I wouldn't bend over backwards, do all this just to solve that problem. No, I wouldn't. However, what if I'm doing a bunch of other crazy stuff in here, and it's not full, integral units of the period of the main system clock, and I'm doing fractional things, and it's moving around, and weird things are happening. Then I got to recalculate whatever the delay period between here and here is and put that in my code. And you can do that. It's not a big deal. Yeah, sure, you can. But when you edit your test bench, and this is, okay, so now we're back to the big point. If I play around with this, I still want a rising edge on T1 to start my I/O cycle. And this is the simplest, dumbest, sure-to-work way to get there. Okay, that's number one. Number two, if I do this, then I know that this has already happened because I waited for phi to go high. I did not wait, if you put a pound something or other in here and just wait another period or a half a period, and then simply know, and that's where I was going with this a minute ago, simply know that there must be a T1 rising at this point in my code. If I wait a half a period, that is a true statement. However, if I waited a half a period and then did this, that's different than waiting for phi to go high. Because I'm now waiting for phi to go high and have been announced to everyone before proceeding. Phi goes high in a non-blocking assignment right there. And then I proceed. If I just put a pound half a period here and proceed, I may proceed before phi goes high in simulation. In fact, I most certainly will, because this is non-blocking, which happens at the end of that time step. If I simply said wait until that time step begins, which is what I would be doing if I said wait a half a period here. Are you following me? This is a big deal. All right. So by doing this and having a non-blocking assignment here, I know that the non-blocking assignment has completed and that every other always block and this code right here is all ready to go right now as a result of phi already having been changed and assigned into the phi value at the end of the simulation period, which is what happens with a non-blocking assignment. If this is not something that's ringing yet, you may want to pause this, go back and listen. This is the whole core of this recording today, all right? You want to make sure that in your test bench that this takes place as if it were inside of one of those, always blocks in a sequential circuit type of design so that you go at the right time. If I did this with a non-blocking assignment and I just put a delay in here, then this value could change in that time period, but before somebody consumes it. If I do it like this, after the phi clock has risen, then it happens at the end of the time period. I mean, if that's what I really want, and this is really what I want in this scenario, all these signals should go and become their active states in a synchronous fashion so that all the other modules can count on the fact that the values are consistent, even if all the always blocks run in random order, which is what you get with a simulation in Verilog. If I do this, then I'm giving my test bench the same respect as I do all my modules when I carefully code a sequential part of the circuit and the combinational part. Okay? That's what's happening here. That solves that problem. The other one is maintenance. Okay? And that's the other big reason we're here today. How do I maintain this code? And still, this just has to happen at the next T1 raising, and I don't want to have to change all the values and all the delays because some dingus wants to put a £5 in here and do something else in here, okay? Then everything else would slosh down and have to subtract 5 from here, or God knows what it would have to do, you know? It might, in fact, if I had delayed a long time and did something in here, I might have to reorder my code to get it to come out right. No, big pain in the butt. You don't want to do that. Okay, just wait on the next rising edge and move on. That's what this is doing. So let's look and see how this marker works and what's going on here. Now, this is just Verilog, okay? And we've talked about this before, but here's an application that, you know, if you hadn't thought about it for a while, it obviously only works for simulation because these delays do not apply in any way, shape, or form to synthesized code, okay? So, and I don't give a lot of thought to simulation. I always think about the synthesis. And so sometimes I'm lazy and I don't really reason this out. So welcome to the club if you're in that camp with me. So let's look and see what's going on here. And everything else in this file is a variation of what we got right here. Okay. So let's look at this. We wait until phi goes high. In the simulation, it has already gone high by the time I get here, like I said. Then I set the marker 1 with a non-blocking. So if anybody uses this, and nobody does because it's just a marker, it will change its value along with everything else that happens synchronously after phi goes on that rising edge. Like I said, if you have a bunch of other modules doing this in synchronous circuits, it'll behave the same way. And for the same reason, which is to make sure that you have an orderly simulation. Okay, now let's look at this. I say set the marker to 1, true. And we know it works because you can see it in this waveform right there. We're looking at this code right now that makes this guy right here, okay? Rising edge. After this rising edge, set T1 high. And then I say wait for a period of the clock and set it to 0, and this is how I do that. Now, notice I don't just put a delay here and then set the marker to 0. Now, this is this is style now. I found that I had a real big mess in this test bench because I was using a really crappy style, and I was just putting delays and then doing stuff and delays, doing stuff, and I can do that. But oh man, it started getting really ugly. So let's think about this technique here for a minute. What does this mean? Okay, this says right now, because there's no delay here, right now, schedule an assignment that's going to go into T1 marker. And what goes into that marker is what happens over here. So what you're really doing when you say this is you're saying after this much time transpires from now, put this value here into T1 marker. And because it's a non-blocking assignment and there is no delay anywhere in this, on the left-hand side of that assignment, this is non-blocking and you immediately go to the next line. So what I'm doing is scheduling a 0 to go into that variable in the future, 1 period from now. Okay? That's why this thing falls over here 1 period into the future. We look at the code, I don't have, wait until the thing goes down or rises, or don't, wait until there's, 52 nanos later and then make it go low. No. Right here, right now, I say, in the future, make this so. This cleaned up my code a lot, okay? This is just standard stuff, but it's real useful, okay? So this will reset the marker in the future at this much time forward from now. Now in here I say AN1, use the same technique. 12 nano into the future, set it to 81 in hex. Okay? Well, that's because the timing diagram said that this address can change, after T1, before T2, somewhere in here, and I stuck it in the middle of T1. Nominally, that's really when it's going to happen anyway. Worst case could be over here. What did I say? If this was running at 20 nanos, this would be 50 long with a 5 nano setup before that, so it would be 45 in here. What did I say earlier? 40? 50 minus 5 is 40. Yeah, right. No. Worst case, this could be 45 in. But it also guarantees that IO rec, worst case, will be over here. Yeah. So it could be, yes, it could be 45 nanosecond after the rising edge of T1, worst case. In this scenario, it's going to go 12 forward from the rising edge of phi, and then it's going to get a value, and that's why you see the 81 right here. In fact, if I put my marker, here we go, let's middle mouse this guy, put a white guy there, and what do we got? There we go. And let it snap to grid in here. What do I got? There's my 12 nanos. All right, so I got, I'm marked on the rising edge of T1, rising edge of phi, and 12 nanos later, the address becomes stable. Somewhere in that code, we'll also see the data bus go stable, and we can measure it at 32 nanos. So this is one of the reasons I think it's nice to have an, oops, I keep scrolling this, the actual nanos on the grid, because you can use this and say, how long is this in my simulation, to see if I got it right, if I was thinking clearly, something shows up, some ludicrous value, then you can sanity check it. So that's what's going on here. So what do we got? We say wait until the rising edge of phi. And then inside here, I just put everything that's going to happen before the next, before the negative edge of phi. I schedule everything relative to the beginning. I said that not very. Let me restate. I schedule everything that needs to take place that is referenced at the rising edge of phi in T1. Notice, and the reason I stop myself is notice that this assignment takes place way later than even this. So I'm scheduling this to happen, because it's an entire period later, on the rising edge of T2. This assignment completes all the way down here, along with this taking place. So, well, and that's scheduled to be in the further into the future as well. So it takes place on this pos edge of phi at T2 is my point. So that's actually kind of neat. So when you're looking at your timing diagram here, and I say, well, and address is a bad example. The good example is the IO rec and the write, which are both, well, write is based on T2, but IO rec is based on T1. What is it? The falling edge of T1, in fact. As drawn in here, this is actually a very bad example for what I'm about to say, and that is nothing is based on the rising edge of T1. Although in my simulation, it's hard, I don't think you can say negative 10 nano from the falling edge of T2 or something like that. Correct me if I'm wrong. I'm not going to look it up. I'm not going to test it out. I'll give it, that's fodder for the viewer. Somebody go look that up and prove me wrong, please, actually, because it might actually be handy to be able to put a negative time on one of these non-blocking assignments. Oh, you should have done this. It'd be kind of hard to read that code. But, I mean, logically, theoretically, it would make sense. It could make sense, I should say. Anyway, so what do we got here? Pos edge of phi. We're going to set things up in my marker in the future, and I have arbitrarily chosen to set the address bus valid halfway through the positive phase of T1. Then on the negative edge of phi, the T1 falling, that's the edge where we see the data bus, the IO rec relative to that, right? So down here, what do we see? Here's IO rec, right? Worst case is 25 nano after the fall of T1. And this line goes down here and says number 23. On the cheat sheet, it says less than 25 nano after the falling edge of T1. So this technique then is arguably very obvious in this scenario kind of what's going on. So on the negative edge of phi 1, 5 nano into the future, do this. 15 nanos into the future, do that. And I'm using positive logic in this test bench just to keep my wits, because if half the stuff's positive, half's negative, this is hard enough to do as it is, people. So I usually model everything in positive logic, and I let the compiler change the logic when it actually is implemented, because it will do that to optimize the circuitry inside the FPGA if it turns out to use less LUTs and gates and things like that. It's smart enough to do that. If not, get another synthesis tool. Okay. All right, so on the falling edge of phi into the future, we do these things. And I chose nominal realistic values, and I put some comments in here. On the falling edge of T1, the spec says that data should happen less than 25 nano. I did it at 5. IO rec should be less than this. We did it at 15, and then on T2 rising, we have the right signal, worst case 25 nano, after the rising edge of T2, number 22 there, okay? So this is less than 25 nanos. All right, so that gives us these things relative to these edges, expressed in my test bench with what I would argue is probably the least amount of code. I had all kinds of twisted stuff in here. And these things grow. I mean, we all been through this. So if you following along and you looked at some of these test benches of some of my code segments, some of them are pretty nasty, and I left them that way. I didn't clean them up. I'm sorry. I'll try to respect the viewer a little more and myself a little bit more in the future as we go, and use this technique, which is fine when you're dealing with synchronous circuits, which you normally are. I mean, face it. Anything significant and interesting in Verilog is going to have synchronous stuff going on. So this should create a much easier to maintain bunch of code. To finish her off, what do we got? We wait for T3 or TW to pass. We don't do anything. We wait for T3 to rise, T3 falling. This doc is wrong. Oh, no, it's not. Neg edge. It's unfortunately that neg edge and pos edge have the same number of letters. Wow. I might go ahead and just so that I can see. For my eyes, that's easier to read. Whatever. You know, you got to be able to read the words. I'll get my bifocals out next time, okay? But at least the comment over here stands way out. That's actually why I noticed it was different. Okay, so why do we do this? We wait for T3 falling edge. We're going to wait 14 nanos to turn off IO rec, and we're going to wait 12 nanos to turn off write, because there's the falling edge of T3 and IO rec, number 29 here, and number 25 are, less than 25 nanos respectively. I left the comments in for read because what I'm going to do is I'm going to cut and paste this and reuse the code in some other test benches. It took long enough to calculate all these values. I'm going to go ahead and keep the doc around and use this to generate, moderately timed IO operations from this particular project from my CPU as I go forward. All right, so what do we got over here? We have when that all ends, what do we do there? And then be careful that write does not happen after the pos edge of phi here. Okay, so here, now we got to talk about not getting cavalier with this. I mean, that looks real easy. Yeah, I'll just throw this together and do whatever I want. Well, yes and no. Notice I waited until neg edge of write here to turn off the address and data bus. And the reason I do that is because the spec gives you, when I say the data bus and the address bus, it says the address bus doesn't go on and off from T1. It's a little annoying. It probably does, but what they're giving you is the time on this line here. It's number 11 after IO rec goes high, and it's number 11 after write goes high for the address bus. That's the hold time. They're documenting the hold time of the address bus is whatever number 11 is. I look it up. It says it's greater than 5 nanos. So your held time on the address bus is 5 nanos after IO-rec goes invalid and write goes invalid or inactive, whatever you want to think there, okay? Now the data is 27 after this line here. This is nice to do with a mouse because you can actually see what's going on. That line goes up and it says that is relative to the end of the write cycle. And it's, what does it say, a number 27. So I looked it up in the chart, and it said greater than 10 nanos, and I throw it in my doc here as well. So what I'm doing here is if I move right around, why am I doing this, right? I could do this based on, phi or something like that, because, let's face it, the address bus will change as a result of phi. I'm sure that that's how the chip is designed. However, the timing is specified relative to the negative edge or the trailing edge of the write signal and IO-rec here, or specifically the write signal for the data bus. The address bus, actually, my code's wrong, is specified, I think, relative to just IO-rec. No, they're both specified relative to write, and IO-rec. Fine. Good enough. I'm going to go ahead and let these slosh around a little bit. This timing is actually wrong because, as you can see, my IO-rec goes inactive 14 nanos after the negative edge of phi, and write goes 12 nanos. So this is actually 2 nanos later than write, and we're guaranteed that the address will be 6 nano or whatever it is, 10 nanos or something like that. Is that right? 10 nanos? I don't remember. 5 nanos, yes. I'll read my own doc after the IO-rec and the write. So if I do this, and I have this number here at 14, this is technically wrong. So what I'm going to do is I'm going to change this to 11, and now my code's right, because it's less than 25. So let's just pull this one back earlier. That way I don't get 10,000 emails. Yes, I was wrong, but this is now right, provided that in my simulation that IO-rec and write, IO-rec never goes inactive after write does, then this is acceptable here, okay? If you said neg edge write, and then you put a neg edge IO-rec and said, well, I'm going to put them both in here, then your problem would be that you have to have a neg edge write and a neg edge IO-rec in that order for the simulation to complete. So if you really wanted to have it done either A or B, you'd have to create a signal here that is the OR of the two and calculate that using a combinational circuit, and then put the neg edge on that and use that. If you really wanted to do this exactly correct, that's what you'd have to do. I'm gonna be a little sloppy. I'll probably regret this, and leave it like this for now, okay? And just leave this all based on the right trailing edge. All right, so what I was just talking about is the order that these events occur, these edges. This is kind of important, and this comment over here also applies. I laughed a minute ago, but now it's pretty serious. If you model the write, and you take more than, this is on neg edge of phi, if you take more than a half of the period of the phi clock in here, then write will not have a negative edge before the phi that is really associated with it. Think about that for a minute. If you model, I'm going to have an extreme, and just for fun, I'm going to move it way over here after this rising edge on T1, which is on phi, right? So then what happens is that this test bench won't work right, because my test bench must wait until there's a negative edge on write to do this, and before it starts waiting for a pos edge on phi. So what will happen is that this pos edge on phi will work, but what we would be doing then is we get the wrong pos edge, because really what we're doing here is we're waiting for the positive edge on the T1 of this next cycle over here. All right, look at what's happening here. Here's where T1 marker goes on and stuff like that, and here's where we got the neg edge of write. And then we clean up the address and data bus after that time, right? So here's my neg edge on write. Here's write. There's the negative edge. I'm going to put a white marker there. don't know what B stands for, the block or the border, I don't know. So there's the B, and then we zoom in a little bit and be more obvious. You can see that the what is it? The data is over here at there's your 12 nano, and the address ends at 6 nanos after the write terminates. You can also see, if we zoom in, that IOREC is over here. And remember, I just tweaked the code there to move that over here so that this diagram is not incorrect, because these are just nominal times anyway. The worst case times are over here. It's just the same thing. I just chose different values. And as you can see, if you kind of look back, the address and data bus give you all this lead time before the IOREC and the write. But over here, you can see everything's much tighter. IOREC and data are active so close to when IOREC goes on, and IOREC goes high on the rising edge of T2, and write goes active almost at the falling edge of T2 in the worst case scenario. And this over here, the moderate cases, things are happening a little earlier, a little more setup, and a little more hold than they do over here in the worst case. All right, so I'm just saying. So that's why I did the modeling twice, but that's not paramount to this discussion right now. What is paramount is this order of these events, okay? And my point was that if you have this on negative edge of write, if this thing exceeds your 25, 27, or whatever the number of nanos that half a period of phi is, because it starts on the neg edge, if I wait too long here, this negative edge won't happen until after the positive edge of the phi that I really want to wake up on, which is here. And that's where that last tangent started off at, right? So if you move the falling edge of write too far back, you can screw up your timing using this particular technique, all right? I'm just saying. So you got to keep an eye on that, because I'm jumping around between positive, negative, and now I'm waiting on write instead of phi. But because I know that this thing should never be greater than, it turns out that my 18.5 megahertz, this thing will always be less than your 27 nanos, which would, if it was greater than that, then this would happen too late, and I'd have a problem over here, okay? So I use this technique, by the way. Well, if it's so problematic, why do you use it? Well, I use it so that I can play with this number, and I can keep these alone, because remember, the spec is that A in 1 and D in 1 happen as a result of when write and or IOREC move. They're not spec'd in terms of phi. So I went ahead and said, let's do this in terms of when write has its trailing edge. That's why it's done this way. Okay? But, I got to keep in mind, make sure that trailing edge happens in the bounds that it should occur. Otherwise, everything else gets out of whack. So that could be one of the problems if you're not paying attention. So what do we got here? We're going to wait for the next rising cycle, and I simulate an instruction fetch in this particular scenario, and then I wait another period of... I'm just wasting time here, letting the clock tick, showing these T1s, that's those, in this particular CPU. If you did 2 I/O operations back to back in the machine instruction, an I/O operation would have an opcode fetch, an operand fetch, and then it would do an I/O operation. So it would take, there's the leading edge. Oh, let's do it this way, right? Put a border there, and then this is how long one I/O operation instruction would take at this clock rate on this machine, 540 nanoseconds in its entirety, if I do it using a regular old output instruction with an immediate operand to hold the port number. Okay, so that is why I wasted this time. You get a visual reference. In this particular application, the reason I do this is because when I'm evaluating the modules under test, they have operations to do as a result of an I/O operation. Then they're clowning around with stuff like that before they're ready for another I/O operation to take place. So I wanted to have a test bench that had the right amount of clock ticks specifically between these two operations to make sure that I had enough time, enough clocks in my circuit that I'm modeling to finish its job before we get over here. All right, so that's why I wasted that time. After here, I also kill some time just to frame out my waveform diagram. So that's why these are there. And I do another instruction. This is all the same stuff, and I'm going to go over any of the details in here other than to just observe that in here I change all these values to be the worst case times. And I already mentioned, if you look at the timing diagram here, these are all smashed up worst case times. These are all, more set up and hold and more optimal case times. Now, before we go, I'll do you one more favor. Let's look and see to make sure that we understand exactly what happens when we do this. Okay? I Googled around before I recorded this. I try to, find existing references and stuff like that before I record my videos to make sure that I'm not a complete nitwit. And when I recorded this, I thought I was a complete nitwit because there's a lot of really bad information out there. Okay? So test your own knowledge and your own simulator tools before proceeding. Okay? Now, I checked this. I believe it to be true. Let's put this code in here and look what this does, and then I'll let you go. So what do we got here? When is the right-hand side evaluated when we do these? Okay, in this entire test bench, everything over here is a constant. In this case here, it's a constant as well. This is not a constant. Or more accurately, this is not a constant, okay? The delays are constant, but the value over here, in this case, it's not constant. So what does that mean? I'm actually going to, down here I put phi into the T1 marker. Up here I put 0 into the T1 marker at 3/4 of a period after the after the positive edge of phi here. All right, so what this is going to do is it'll put a T1 marker just like we see all these others here. But this one, in fact, you can see it. This is it right here. It's only 75% of the way. This is 100% of the period of the T1 clock. So this extra one in here, I must have compiled it before I ran this, and with the comment off. This is the that test marker. So what this is doing is it goes 1, waits 3/4 of a period, goes 0. So this is executing the code you see right now. Let me go ahead and make sure that that's still true. I already have the thing running, so all I really need to do is recreate the VCD file. Come down here. I mean, sometimes you open up this viewer and it takes you 20 minutes to get all the waveforms in the right order and everything way you want it, and then you're like, oh, I got to redo it. And, you don't want to close it and start over. Giant pain in the butt. This here is a little reload button, which will reload the entire VCD file. And this button over here is the size it to fit on the screen. And I'll sized it like an idiot. But the reason it just sized it like an idiot is because it sized what I have here. Okay, if you do that, get rid of the white marker by just clicking the middle mouse again. If I click it, it goes on, click it on itself or somewhere else, it goes back off. When you do that, just turn it off and then redo this. You see the whole picture. Okay, so that's the code we're looking at right now. And that makes sense because of what we were just talking about. Wait a while, waiting in terms of phi, the period, that is, that's fine. What if I do this? So now what's going to happen? Is this going to assign the value of phi 3/4 of the way through the period? Or is it going to assign the value of phi when it schedules the assignment to take place later? Which we know are two different values. We just waited for a pos edge of phi. This is non-blocking. So when this thing runs, phi is 1. It is high. So the question is, does it wait and then look at phi in the future when we know phi is low? I didn't reload the waveform yet. So what happens is, here's your 75% of the time when I had it hard-coded to 1 and then to 0. So here's phi, right? Here's my phi line. It's not a cat. It's the line that is marked phi. It's high for half the period and low for half the period. So is it sampling it over here when that statement is first encountered, or is it sampling it being phi over here when it does that assignment? Okay? In other words, is it going to still look like this when we're done, or is it going to go high and then stay high until somebody else changes it, which no one else does? Okay? Quiz. What do you think it's going to do? I had to actually think this one out for a minute. And I actually went around and looked at some papers to make sure I'm not giving you crappy advice, because this is one of the things where there's a lot of crappy advice. It went high and stayed high. What does that mean? It means that this thing, and this is what the more authoritative paper sources said. I'll show you a paper, and I'll put a link to it in the description below that we should all read, perhaps twice before doing this some more, where they talk about this stuff. So clearly what's happening is phi is sampled when this non-blocking assignment is scheduled. Then it is scheduled to take place 3/4 of a period through, and the 1 is assigned back into T1 marker, which is why it doesn't change its value. It does not put a 0. It does not put phi at this time into T1 marker. It puts phi at the time this was executed into T1 marker at this time. Okay? All right, are we good on this? Because that's actually, pretty, that could be subtle, if you're doing anything other than assigning constant values in your code. Now, I only assign constant. The whole thing, all I ever do is schedule a constant to be put in there, constant to be put in there, more constants to be put in. So in a test bench, probably, I can't imagine, in any simple test case, I always just assign constants over the course of time. So the question may not even come up until someday when all of a sudden you don't realize what you're doing here. So good prize for those of you that powered through this entire video. There's the secret quiz of the day. This is evaluated before the delay and assigned after the delay expires. All right, so let me know what you think. If there's any better way to do this, or if I've completely blown it, let me know in the comments below. I eagerly await your thoughts. Thank you. I'll see you later.